Introductory lecture on COMSOL. So we're going to go through the main interface and the different windows that COMSOL has, and talk about the structure and what is involved in setting up a model. And I will just go back and forth between a tutorial that I have here and also a real model in which we did some heat transfer calculations. So if you look here on the bar, you'll see that when you get to COMSOL, you have an area that is called the initial model tree, and the tree has only two nodes that come with COMSOL. The two nodes of the tree are the global definitions and also the results node. So if I expand it here, you'll see that I have, once you open up COMSOL, then you will have these two nodes coming that are ready to be populated. As we build the model, two additional nodes will be added, and those are going to be the model node, and then after the model node will be how you're going to do the computations in this model. And each node will have subnodes, and the subnodes will contain specific information that we will expand as we build up our model. So if you look at here, you'll see that I have on the left side, there's a model builder window, and the modeling process is basically controlled through this window. And then you have another window, and this window here is the model wizard window. And the model wizard window, it allows you to select the space dimension that you need, either 2D or 3D or 1D or axisymmetric. And also it has another tab that allows you to select some models that are already stored in the COMSOL library, so you don't have to redo the geometry. And this is the model library that you'll see here. So if we look here, we find another tab. If you just click on it, you will be able to get any of the models that already exist for further studies. In addition to that, we have one more window, and this window is the graphics window. And the graphics window is comes like a blue screen, and on that you'll be able to have different views of the geometry, the mesh, the results, and then you will be able to select the various views from there. So if you want to look at, for example, let's look at real model here, and you see on the right hand side here you get the results, and the results are displayed as temperature at a particular time. So this is a transient temperature calculation with COMSOL, and on the left here you have the additional nodes that were added to the global definition and the results. So what comes with the system is global definitions and results, and then later we add another node called model, and another node that specifies what you're going to study with this particular model. So moving on to the settings. You go to the settings window, and in this window you enter all of the specs of the model, the dimensions, the geometry, the properties of the material, the boundary conditions, initial conditions, all of the information that are needed for the simulation. And you see here this is expanded. Once you added, we added a model after we have the tab that selects the model. Then we would insert this additional node called model, And then if you right click on this additional node, then you will have subnodes, and the subnodes you can see here: definitions, geometry, materials, and then the type of physics that you want to study, solid mechanics. And then under solid mechanics, if you right click, then you get linear elastic material, and then you specify the boundary conditions as free boundary conditions, and the initial values also are specified here. Note that there is a D on top of the representation of the tab, which means that these are default values that you can change. So in addition to the definitions, geometry, materials, physics, and the mesh, you have one additional subnode called mesh. And this subnode, when you right click on it, you will be able to control the mesh size. You can make it finer or coarser, and that determines the number of degrees of freedom that you'll be solving in the model. Once we created the model, then we want to specify what we're going to study in this model. So if you notice here in this particular setup, the model that we have was determined as a three-dimensional finite element model for solid mechanics, and the material is described as linear elastic, and it has free boundary conditions with some initial values, and we selected the material for it, and we have specified the geometry for that particular model. And then we decided on the mesh size, and now we have to decide what we're going to do with this model, what we're going to study. Are we going to study a transient response, like time-dependent response, or a steady-state response? Here in this case, we wanted to have a study, and the study is we can actually use the same model for different studies. So study 1 here, we decided that it will be stationary, and we will get the results for a stationary solution. And then after the study has been performed, which means a solution of a large system of linear algebraic equations, so that's what the console will do, then it will give us the results that we can display. And the results node, we can expand it, and as we expand it by right-clicking, we will be able to decide what kinds of results we will get out of this. Are we going to display it as graphics or as tables, or are we going to post-process the results, and so on. So this will be clear as we move on to the more realistic model that I will show. So let's just continue here to look at the final window, and the final window is the plot window, and the plot window is what we've seen here. For example, in the real model here, the plot window, it will show like here if the results, for example, you have a 3D plot and you have a surface plot. So the plot window that you'll have is this window that will give you a 3D color representation of the temperature distribution. We have also one additional window in the bottom here, and this window is more of diagnostics, like we get messages in here. For example, here it says avoided 245 inverted elements by using linear geometry shape order. These are messages which console either encounters the problem, solves the problem in the process, and gives you an idea about what the solution was. There's another window that gives you the progress. When the calculations are running, you will see a bar, and the bar will give you an indication of where you are in the calculations. And a log window, which logs all of the steps that console is going through, and then a table, and the table can give you coordinates x, y, z, and the value of a parameter. For example, if you click on a point, then the point here you will show the temperature, the coordinates of the point, and the temperature at which we obtained these values. So these are all useful windows that we use for additional information. In addition to this, if you expand, for example, the results, if you look at the results node, let's look at the results node. So we have a node here called the results node, and it has data sets, it has derived values. For example, if I need to take the temperature and for some reason I want to square it, or I want to input that into another function, I can do that here as a post-processing step. Tables, I can create tables for the output results in the form of tables for reports in the future, and I can also create 3D plot groups. So each group will have a variety of plots that you can have: surface plots, line plots, and arrow plots that show, for example, vectors such as the fluxes. And if you click on the surface plot, then it will give you what are you plotting. For example, here the temperature, and then you can change the temperature to something else. From the heat transfer, for example, you can change it to energy, you can change it to heat source, and so on. Many different things that that you can have. You can also plot the mesh, and so on. So you have the expression to plot, you have the units, and a description. And then you also have ability to export the data, and you can export the data in the form of an animation. And the animation here is a movie. So your output type is is image sequence or a movie. You can choose a movie, and the format here is GIF or AVI or Flash. And then you give it a file name, and then you have the sequence of the solution, where you select the times, like here 0 time, 10 seconds, 20 seconds, and so on. So you select all of them all the way, and then you, in this case, you can find a transient solution for this movie, or the transient representation for the temperature evolution as a movie. So this is what we have here with the basic interface for COMSOL. One more thing that we can talk about is the preferences, and the preferences settings, they affect the modeling environment. So you can access the preferences from the options menu, and that gives you, for example, the graphics. If you have a very heavy-duty model that has a lot of elements, then the graphics can be very difficult if you have a graphics card that is very slow. So you can select the rendering. For example, here is DirectX 9 rendering, but you can select the rendering in different ways. And the different ways that they have is OpenGL, DirectX, and software rendering. And apparently DirectX is not available for Mac, but it is, so you can use for Mac, for example, OpenGL or software rendering. OpenGL is if you have a faster graphics card. Software rendering is kind of slow, and then the motion of the features, or if you just have rotation or movement of the model itself, it becomes kind of slow. So that all depends on the graphics card that you have. In addition to this idea now that we start with the two main nodes, is the global definitions and the results, and these two main nodes are part of the primary node, or the node that defines the name of the model. And the name of the model here, it comes as called untitled. So this untitled here, you can change it to your own name for the model, and that will be the root for all of the trees, for all of the nodes in the tree. And then from this root we have now 4 nodes, the global definitions node, the results node, and then we insert 2 more in between, and the 2 more is the model node and then the study. And then by right-clicking on each one of those, then we have a whole bunch of subnodes that we can control the flow of the computations. This is now shown clearly. Now once you build your model, then you have the main trunk of the tree, and then these are 1, 2, 3, 4. This is main nodes in the model, and then under each one of them we have the subnodes. So okay, I think the best way is to go through the model that I built for the heat transfer, just to show one step by step. So here we're talking about the model node, and then we can have model 1, model 2, so you can add different models, study 1, study 2. So if we look at the heat transfer idea here that we have, so let's see, we have model 1. The model 1 under this main node there is subnodes. The first subnode is definitions, and the definitions is that we're defining the boundary system, and you can see the colors change here to define the system that we're studying here. And then we're defining the view, and the view has camera. You can define where the camera is and the light source and so on with that. But these are more details in terms of how you're going to proceed with the calculations. So normally we use the default values for here. Now the next subnode is the geometry, and the geometry subnode, it has an import because you can build the geometry inside COMSOL, or you can import it from another CAD program like SolidWorks. So in here, if you want to import it, then you can browse and import the geometry from a CAD program. And if you have different pieces that come from the CAD program, you can form a union between them. For example, I had this cap, and the cap I have an assembly, the adapter that would be assembled to the cap, and then it is welded by this weld in here. So all of this will form as a union between the 3 pieces in COMSOL. So once I have now defined my geometry, I go to define the materials. And the materials, if I right click, then it gives me, like if you right click here, then it shows you can open the material browser, or you can add your own material. So here we chose from the material browser the material A, this is a steel A537 steel, and you define it for a particular domain. So if we have a domain, you can define the material for either boundary or an edge or a point or domain. So if a domain, we define it for domain 1, which is the cap, and domain 3, which is the adapter. Now the material for the weld is different, so we added another material, which is another steel, and we defined it defined it for domain 2. So if you click on this domain 2, then you see that material is defined here. So once we have defined the materials for the different domains, we are now ready to add one more node to the model, which is the physics. So the physics that we study is heat transfer. We selected heat transfer physics, and heat transfer, you have to define also what domains you want to use this heat transfer physics for. Here we defined it for all domains because we have 3 domains, 1, 2, 3, or you can have manual to select each one of these domains separately. And the heat transfer model comes in with a default, which is a heat transfer in solids. So it's selected on the 3 domains again, and it solves for the temperature, and it uses global coordinate system, and then the material parameters for the heat conduction is the K, the thermal conductivity, and that comes from the material that you chose or user defined. So here the conductivity comes from the material we chose. Additional properties are thermodynamic properties like the density and the specific heat, and those are all coming from the materials that we selected. Now we have to specify the boundary conditions and the initial conditions. So the boundary conditions, these are the default is all thermal insulation. So everything here, all of the boundaries are thermally insulated, and if you click on one boundary, then it should show you where it is on the graph. For example, boundary 1, then it is this left part of the cap, and it is thermally insulated. So it comes as thermal insulation as a default, but we can override it. So it says here overridden by adding, for example, other boundary conditions. For example, if I have heat flux, then I specify what is the heat flux that comes. I have a heat flux coming to the weld zone, and this heat flux comes to zone 7, which is this domain, and zone 9, which is this domain, and zone 11, which is this domain, and so on. All of these come into pieces in which we can specify the heat flux separately. And the heat flux is specified here as 3 times 10 to the 6 watts, but it is multiplied by a logical function here, and the logical function is t less than 60. This means that it's like a step function. So the heat flux, when this function is true, then you get 1. When it's false, then you will get 0. And this means that the heat flux is only applied for 60 seconds and then cut off after past 60 seconds. So the heat flux is specified on these boundaries. Also, we have convective cooling, and the convective cooling is specified on all of the other boundaries, like the cap is convectively cooled by air, and the heat transfer coefficient that I defined here is I found it from the literature. It's 35 watts per meter square, and the external temperature is room temperature, and therefore I have defined all of the boundary conditions. The initial values is how you start the calculations, and the initial values are given for domain 1, 2, and 3. All of the initial values are 293.15, which is room temperature, Kelvin. These we can also change. So that defines the physics, and then the next subnode is the mesh, and the mesh we have decided on the size of the mesh. So the size of the mesh here is predefined. It's a coarse mesh. You can make it fine and finer and so on. For example, if I wanted to make it finer, and then I have to build all of the mesh again. And when you build it, it just takes a little time to process the information and build the new mesh for the entire model. And you note here that this is not highlighted, so it is going to be highlighted once the meshing has been finished, and then it meshes the 3 different domains that we have specified with a finer mesh. So this is the domain 1, which is the cap. This is domain 2, which is the weld, and then domain 3 is the adapter itself. The mesh that is size now is defined. Then the type of the mesh that we have is a free tetrahedron, and the free tetrahedron, it means that you have pyramids in 3-dimensional space, and the solution is defined in each one of these pyramids as the temperature and the heat flux, for example, represented by finite element method. So this is the free tetrahedron, as you can see here. And if you now look at at this window, you can move the model with the right click of the mouse. You can move it around so you can see the mesh distribution. And if you the left click is you can rotate it. The right click, you can move it, translate it. So here's right click is translating, and here is left click is rotating. And then I can also zoom on the particular model, or I can bring it back to the extent. For example, if I just click here, then it brings the model, the entire model. You can see it here within the window. If I zoom in, then it can give me more detail, as you can see here. And then I can rotate it again. I can zoom out from the model. So this is the mesh idea. Now, if you get to the idea of the study, the next node is, now we have finished the model node. Now we go to the study node. The study node, this is a transient problem, so we have a time-dependent calculation, and it has a solver sequences, and the solver configurations is what defines whether we want to solve in direct form or by stepping through the solution. There are more detail that we'll be able to come back to these details later, but essentially if you go to the time, then you specify the range of the solution from 0 to 500 seconds in 10 seconds time step, and therefore the solution is going through the system and doing the integration and giving us the results as a function of time. So this is for the solver sequences. And once we have defined the study, then we talked about the results node, and it has many subnodes, and one of them is the important one is the 3D plot group 1, which you can make surfaces and lines and so forth, or you can have another node that exports animation results. In addition to the plotting and derived values and tables, you can also make reports directly from the study results. And I think this gives us kind of an idea about the interface with COMSOL and how we started. And in the next lecture, I'm going to go through a more specific example on how to do structural mechanics of a wrench. We'll see you in the next lecture.